Hello, everyone, and welcome back to the Math Puzzle Crash Course. I've got a little bit longer video today. I wanted to cover number systems, and we'll go on and take a look at which ones we're referring to. I've got several here. The first one should be very familiar, called the base 10 or the decimal system, which is the system that most people should be familiar with. We often take for granted that the number system that we're using, it's known as the decimal system or base 10. This system's made up of 10 distinct digits. We got 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Should seem pretty obvious to most people. These 10 digits are used to represent any number, like the number 563, uses 5, 6, and 3 digits out of that. So when we hear base 10, this also refers to the base number when we're using exponents. It's the number that ends up being multiplied by itself. So in the base 10 system, naturally the base is 10. So it becomes a little bit easier to understand what we're talking about here when we see an example. For example, let's take the number 456. This number can be represented using exponents as 4 times 10 squared plus 5 times 10 to the first power plus 6 times 10 to the 0 power. So if you look at that, 4, 5, and 6 are referred to as coefficients. 10 is the base, and the numbers 2, 1, and 0 are exponents. So you have 4 times 10 to the second plus 5 times 10 to the first plus 6 times 10 to the 0 power is 456. So if you're familiar with exponents, just remember that 10 squared, or 10 to the second power, is equal to 100. 10 squared is the same as 10 times 10. 10 to the first power is simply equal to 10. 10 to the 0 power is equal to 1. And any number to the 0 power is equal to 1. So once again, 4 times 10 to the second plus 5 times 10 to the first plus 6 times 10 to the 0 power is 4 times 100 plus 5 times 10 plus 6 times 1. So that's 400 plus 50 plus 6 equals 456. So once again, yeah, that base 10 is referring to the base here, this 10 number. For larger numbers, the exponents are increased to represent thousands, 10,000s, 100,000s, and so on. So let's say we have the number 4,456,598. Well, that's represented by 4 times 10 to the 6th power plus 4 times 10 to the 5th power. And these all just, these exponents just decrement by 1. 4 times 10 to the 5th power plus 5 times 10 to the 4th plus 6 times 10 to the 3rd plus 5 times 10 to the 2nd plus 9 times 10 to the 1st, and finally plus 8 times 10 to the 0th power. So this is a good thing to remember for all number systems, not just our base 10 system, but again, you look at this example, we have 4 times 10 to the 6th. The 4 would be our coefficient. This 10 is the base number, which in our case we're using base 10 or the decimal system. This number 6 is referred to as the exponent. So keep in mind these when you see these types of problems, the coefficient, the base, and the exponent. All right, so we'll move on to another really common numbering system. Instead of base 10, you may have heard of the binary system or base 2. The binary system is very familiar to engineers and computer scientists. I've worked with it quite a bit. Binary number is just a number that's expressed in the base 2 system that consists of only two symbols. There's only two symbols here, 0 and 1. So in the base 10 system, we had 0 through 9. We only have 0 and 1. So Yeah, if we're given a binary number, you may have seen problems like this. You know, you've got a binary number 11010110, and you would need to know what the decimal equivalent of that is. Well, we already learned previously what the coefficient base and the exponent are. We know this is a base 2 system, so it should be pretty simple. Um, you know, if the base 10 system is a base of 10, the base 2 binary system, well, it must have a base of 2, right? So yeah, so we take this problem here, this binary number, and we break it out as we did before. It's 1 times 2 to the 7th. Remember, it's a base 2 system, so we're always going to have 2 as the base. Coefficients here are either going to be ones or zeros. Those are the only two symbols that we're using. So and we're all the way out here to the 7th position. This is the 7th position, so it's represented here. It's the most significant bit. 1 times 2 to the 7th plus 1 times 2 to the 6th plus 0 times 2 to the 5th plus 1 times 2 to the 4th plus 0 times 2 to the 3rd plus 1 times 2 to the 2nd, or 1 times 2 squared, plus 1 times 2 to the 1st power, plus 0 times 2 to the 0th power. So if you solve each of these and solve each of those, you get 128 plus 64 plus 0 plus 16 plus 0 plus 4 plus 2 plus 0. And that equals 214 in decimal format. So 11010110 is equivalent to 214 in decimal format. So yeah, on a Windows 10 or 11 PC, you can select the programmer mode calculator, again, the programmer mode, and enter the binary number and check for the decimal result. So if you go to the calculator app on your computer, Windows computer, you'll have this programmer mode that you can select. I think the default is normally the standard mode, but if you select programmer, then you can see here you're allowed to enter ones and zeros here. So you would enter 11010110, and if you look over here, this actually shows you the equivalent values in different number systems. The one we're most interested in, we said we wanted to know the decimal equivalent. Right there it is, 214. This hex we'll get into in a little bit. This is called hexadecimal. The value would be equal to D6. The OCT, that represents octal. That's another numbering system that we'll talk about next here. And the value would be 326 in octal. So these are all equivalent values. Yeah, the next system I wanted to cover would be the base 8 system, or also known as the octal system. Now, the octal system, again, I said is a base 8 system. It uses the digits 0 through 7, so those would be the symbols. The symbols would be 0, 1, 2, 3, 4, 5, 6, and 7. So somewhat similar to the decimal system, but instead of base 10, it's base 8. Um, Now, advantage is it uses fewer digits than the decimal or the hexadecimal system that we'll cover later. So fewer digits means, hey, you can represent larger numbers with less symbols. Um, a lot of times it often makes a lot of sense to cover the hexadecimal system before octal, but we'll just go ahead with this and hopefully it will make some sense. In the early days of computing and devices such as programmable logic controllers, also known as PLCs, um, inputs and outputs to those devices were configured most often in counts of 8 bits or 1 byte at a time. So 1 byte is equivalent to 8 bits. And very large binary numbers can be a lot more easily explained in their octal equivalent. If you've got a 32-bit or 64-bit binary number, that's a lot of that's a lot of writing. You could end up with 64 characters to represent a number. Octal digits can be explained using three binary digits, which helps us to convert those larger binary numbers down to a more compact octal equivalent. So that this table should help. You've got the octal symbols 0 through 7 on the left column, and then on the right column you have binary, 3-bit binary representations of those. So, obviously 0 octal is 000 and using, 3 bits of binary. 1 would be 001. And this again is binary. The number 2 would be equivalent to 010 in binary, and so on, all the way up to 7, which is equivalent to 111 in binary. And you can work those out. You can go back and use the coefficient, the bases, and the exponents that we talked about, and you'll see why 111 in binary is equal to 7 octal. So, the octal system's not as widely used as it was in the past. Often a number that's represented in octal form is shown with an 8 as a subscript to note that it is an octal value. For example, if you have 472 with the subscript of 8, that represents 472 octal. And don't confuse that with 472 in decimal. So yeah, if you have 472 in octal and you break that out using our coefficient, base, and exponent values, you'd have 4 times 8 to the second plus 7 times 8 to the first plus 2 times 8 to the 0 power. Again, remember base 8 means this 8 is our base. So that works out to 4 times 64 plus 7 times 8 plus 2. And that gives us 314 in decimal. So yeah, 472 octal is equivalent to 314 in decimal. Now the following table helps show that relationship between decimal, binary, the 3-bit binary, and the octal formats. So over here I've got the decimal values 0 through 9, which we should all be real familiar with. Here's our binary 3-bit equivalent. You've got 0, naturally 1, 0, 1, 0 is equivalent to the decimal 2. And you'll notice that, as far as octal and decimal, they seem to line up really well up to 7, right? Well, and then of course in octal, we don't have any symbols after 7. So this one here, where we have a decimal value of 8, well, that in octal, that's 1, 0. And then, of course, in binary, it's using 3 bits. We've actually got to have 2 sets of 3 bits. You've got your 000 here and 001 over here. And if you look at how these are weighted, if you break those out again, like I said, using your coefficients, bases, and exponents, you'll see that this does work out to the decimal value of 8. And carefully note here, like I said, that octal 10 and octal 11 are not the same as decimal 10 and 11. But yeah, even with 9, you see the decimal value of 9 is equivalent to 1 octal. And you can see how this 3-bit binary works out. It makes it actually really convenient because, for example, here where we have octal 1, 0, well, if you break these up, look at that. This 3-bit binary is 1. This 3-bit binary is 0. It's 1 and 0, which we have 1 and 0. And over here, in this one, we have 001, 001. What is that? 1 and 1. Here's what that is, an octal, 1 and 1. So, yeah, so keep in mind that octals are very easily represented in 3-bit binary. So yeah, you can see how, again, I'll go through it again here. You can see how the 1, 0 means 1 and 0, 0, 0, 1, and 0, 0, 0. Basically, this is just explaining what I just did previously. Uh, and, uh, I hope this table is somewhat helpful in understanding uh, this numbering system. And, using our binary number example that we had from before, we should really now be able to easily convert it to an octal number. If you start, take this number here, you start from the right and group the numbers by 3 binary digits at a time. So you can see I've got spaces in here. See how I took this number and put it here? I got 0, 1. If I go from right to left, 0, 1, 1. I've got 0, 1, 0, and then I've got 1, 1. Well, note that, I've only got 2 digits on this far left side. You can pad an extra 0 to the left, which doesn't change the value of it at all. Oops, there we go. And you can see here in red, I've added that extra 0 to the left. And why is that? Well, again, remember one of the first things we covered, coefficients, base, exponent. If you have 0 times 8, okay, what would that be? 0, 1, 2, 3, 4, 5, 6, 7, 8. What would that be? 0 times 8 to the 8th. Well, what is that? Well, 0 times anything is 0. So again, this adding that 0 all the way to the left doesn't change the value of this binary number. So using our table from before, you can convert each of the 3-digit binary groupings into the octal equivalent, right? So if you look at that, 0, 1, 1 binary is equivalent to 3. 0, 1, 0 is equivalent to 2. 1, 1, 0 is equivalent to 6. And you can easily see that here because, again, we're talking now here we're talking binary. This is octal. So here we've got 0, 1, 2. You got, this is um, equal right here. This is equal to 4. This bit represents 4 decimal, 2 decimal, and 1. All right, so yeah, again, so your 0, 1, 1, 0, 1, 0, 1, 1, 0 in binary would work out to be 326 in octal. And that's also equivalent to 214 in decimal. Again, another system mentioned briefly before is a base 16 system, also known as the hexadecimal system. The hexadecimal system's, again, a base 16 system that uses the digits 0 through F. Whereas, the decimal system, we had 0 through 9. Here we have 0 through 9, but then we also have A, B, C, D, E, and F. The hexadecimal system helps to lessen the confusion writing out really long binary numbers. Each digit of a hexadecimal value can be represented by 4 binary bits. So what that means is you could have a 4-digit hexadecimal number. 4 digits hexadecimal could represent 16 bits of binary. So you could see how useful that would be. In a large digital system, it's common to have binary numbers that might be, 16 and 32 bits and even larger. And that can look really confusing and take a lot of time to write or to type out. A 32-bit binary number can be represented um, by 8 hexadecimal digits. You can think of the hexadecimal system as kind of a shorthand method of writing out a binary number. And the following table will help us to see that relationship. Here we have got first column is the decimal values 0 through 16. Here we have a 4-bit binary representation. Again, like for the decimal 1, you have 0, 0, 0, 1. Um, Going all the way up here, you got 15 decimal, where 15 decimal is represented by 1111 binary. That's also equivalent to F in hexadecimal. You can see, remember, we said that the symbols run from 0 up to 9, and then A, B, C, D, E, F. So 10 in decimal would be A in hexadecimal, and in binary, 4-bit binary, that's 1011. 1, 0. Now notice here at the very bottom where we've got 16 decimal. If we look at 4-bit binary, we actually need to have two sets of 4 bits. We got a byte here. So we've got 0001, and then we have 0000. Well, what does that mean? Well, as we noticed before with octal, this would be 1 and 0, which easily converts to hexadecimal as 1 and 0. So hexadecimal 1, 0 would be equivalent to 0001, 0000, which is 1 and 0. You can kind of see how that works. So note that in 10, note that 10 or 10 in hexadecimal, excuse me, is not the same as 10 in decimal, as we just said. 10 hexadecimal means 1 and 0 from the 4-bit binary here, which was kind of what I described from the table. You can see how that works. This is the binary represented in 4-bit binary, and then you've got the hexadecimal equivalent of 1 and 0. So yeah, if you're given a number, say like let's say 34AC in hexadecimal, we can quickly convert it over to decimal using that coefficient base and exponent method. You know, we should all be pretty familiar with by now. 34AC is equivalent to 3 times 16 to the third plus 4 times 16 to the second. And remember, A is the same as 10 in decimal. So 10 times 16 to the first. C is the same as 12 in decimal. So that's 12 times 16 to the 0 power. That works out here, 3 times 4096 plus 4 times 256 plus 160 plus 12. That equals 13,484. Yeah, again, note that A is a 10 in decimal and C is 12 in decimal. So hopefully that helps. The use of hexadecimal, you know, becomes really clear when you want to quickly write a long binary value in a shorter form. So let's take a binary example here. We've got this long, I'm not going to read it out. It's, you know, all these ones and zeros. We've got a very long number. It's a 20-digit binary number. We can group those bits, 4 bits at a time. We could start from the least, this would be the least called the least significant bit all the way out to the most significant bit. And what I mean by least and most is that has the lowest exponent of 0, and this will have your highest exponent, which what would it be? 19, I believe, for a 20-digit binary number. So yeah, we could group these 4 bits at a time. We'll show you how that works. Using that previous table that we had, we can look at each grouping of the 4-bit binary and really easily convert it over to a hexadecimal digit. So yeah, we break these up, break up that 20-bit binary number. 1101 would be the same as D. Remember, A, B, C, D. A is 10, B is 11, C is 12, A, B, C, D. So D would be 13. If you look at that value, this is the same as 8 in decimal plus 4 in decimal. And this would have been 2, but there was a 0 here. So 8, 4, and then plus 1. 8 plus 4 plus 1 is 13 in decimal. That's this representation. So yeah, you have D. And if you look at that, this is an easy one, 3. This binary representation is the same as 3. This would be the same as 10 in decimal, or in hexadecimal A. This binary is equivalent to 2, which, yeah, 2. So yeah, what you end up with, this long 20-bit binary number, when you convert it to hexadecimal, is D2A3D. A lot shorter representation and a lot easier to write. So yeah, that's a little basis. There are some other number systems out there. Uh, you know, the ones I've described are probably the most common. One that's common, at least to engineers and some programmers, would be what's known as binary coded decimal, or BCD. That's basically a way of converting decimal numbers over into their binary equivalent. The difference here is that each decimal digit is encoded separately. A decimal number is first split by its individual digits, and then each digit is represented by their equivalent 4-bit binary coded value. Now, 4-bit equivalents are preferred. I believe there's some where they've used 8-bit, but I don't think that's very common. Um, so here we've got a decimal digit of 0. Of course, that's represented with 4 zeros. And then here, 9, if you represent that, remember, if we look at the weighting and you go through your base, coefficient, and exponents, you know, this is equivalent, this 1 here is equivalent to decimal 8. This 1 is equivalent to decimal 1. 8 plus 1 is 9. So basically what you're doing is you're encoding each digit straight into a 4-bit binary. Again, here's 8. 7 would be this. And so it it is useful. So, um, here's an example. You take the number 5,823, which is a decimal number. You could take each one of those decimal digits and encode them into 4-bit binary. So 5 would encode it to 0101. 8 encodes to 1000. 2 would encode to 0010. 3 would encode to 0011. So therefore, your 5,823 decimal is equivalent to this number in binary coded decimal. So some people might ask, well, what's the difference then between this and your standard base 2 or binary representation? Well, remember that the binary coded decimal is encoding each digit, each decimal digit separately as a 4-bit binary value. So 5,823, decimal base 10 is equivalent to this in BCD, but in regular binary or base 2, this would be the value here, and you can verify that. You can go back, pause the video, and double check that. They're not the same. Um, Now keep in mind also that if converting directly from decimal to binary can be done, but it's not nearly as straightforward as encoding BCD. There's various methods for converting decimal over to binary. One of those methods would be to convert a decimal number to binary, would be to determine if the decimal number is an even or odd number. So there's this process you can go through. It's very lengthy. So you take the number that you're working with and say, well, if it's even, you assign a 0. If it's odd, you assign a 1. So the number 5,823 is an odd number, so we're going to first assign a 1. We're going to write that off somewhere. Then the next step you do is, and I know this sounds strange, but you deduct a 1 from 5,823, and then you divide that result by 2. So 5,823 minus 1 is 5,822. 5,822 divided by 2 is 2,911. Then basically what you do is you go back and you repeat step 1 to see if that result is odd or even. So you're going to look at 2,911, see is it odd or even? Well, it's odd, right? So 2,911 is odd, so we're going to assign another 1. So far we have 1, 1 that we should have written off somewhere to the side. Step 3 would be then to repeat the step 2 by subtracting 1 and dividing by 2. And so you're going to keep going through this process. You're going to have 2911 minus 1 is 2910. 2910 divided by 2 is 1455. Keep repeating this. Well, you keep repeating this process over and over until you get a result of 1 from step number 2. And then once that occurs, you're going to write out all the ones and zeros that you've been writing off to the side. You're going to write them out in reverse order. So I'll show these detailed steps here for this problem, and hopefully it'll make a little bit more sense. You'll understand the process. So, first you've got the 5823. Well, it's odd, so we assigned a 1. Then here was where we got our 2911. We subtracted 1 divided by 2. You got 2911. Well, it's odd, so we assign a 1. You take the result of that, 2911, subtract 1, divide by 2, 1455, you get a 1. And you can see how we're doing that. We keep going through a 1. You got an odd number here, you got a 1. And you just keep going down through here. Here in this case, you can see where you've got a 90, right, as a result. So we're going to write a 0 off to the side because 90 is even. And basically we're going all the way down here to where until we get a 1. 2 minus 0 is 2. 2 divided by 2 is 1. So what's our remainder there? Our remainder would be um, we won't have a remainder. 2 divided by 2 is 1. There's no remainder, 0. So then at that point, you write out all those bits in reverse order. You can see how you got 1, 0, 1, 1, 0, 1, 0, 1, and so on. They're all written out here. So that means 5823 is equivalent to this long binary number. So yeah, it's not something I would do very often. It's a lot easier to pick up a scientific or programming calculator to do that and solve that. But yeah, this is just kind of a brief overview on some number systems. Feel free to look to do some Googling and look those up and get a little more info. This isn't really a comprehensive review of all of them, but just kind of a short one. But I hope this video has been helpful to many of you, and if so, please consider liking, sharing, even subscribing. And again, I look forward to seeing everybody in our next video. Thank you.